Welcome back. Now I think we can, now hopefully you have some intuition, and maybe you can figure this out on your own, but I'll show you how to do it. We spent a lot of time on how fast did I throw the ball, how fast was it when I left my hand. Well, let's figure out how high did it go, because that's kind of a cool thing to know as well. So we figured out that the final velocity, or actually the initial velocity, is just equal to minus the acceleration of gravity times time over 2, right? If we say the acceleration of gravity is minus 10 meters per second squared, then this becomes 5t, right? So that's the initial velocity. So we leave, and the final velocity is just the negative of the initial velocity, right? Going back to what we were doing before, right? So the initial velocity, we want to figure out how high did we go. So let's just go back to our basic, we want to figure out this point. We want to figure out how high did this thing go. Right? And that's actually the vertex of this parabola. And if you know the formula for a vertex of parabola, you could do it. But once again, I like to do it intuitively as opposed to memorizing formulas. So we want to figure out how high did this go. Let's call that h. So what happens? I'm going from an initial velocity of vi, and I'm going to a final velocity. Well, not a final velocity. You can kind of call this an intermediate velocity. We go to the velocity of 0. And it takes a time of t sub naught over 2. That doesn't look too good, but it takes, let's say, it takes t over, let's say that it takes t over 2, or t sub naught over 2. I know it gets confusing when it's t sub naught. T sub naught just says this is an actual constant t as opposed to just the variable t. That's all it is. I know it can get confusing sometimes. So the initial velocity is equal to minus g times, whatever we time, whatever your friend gets on the timer. But we also know that between time 0 and time t sub naught over 2, so half the time that your friend has on the timer, the velocity went from this velocity to 0, right? So the average velocity over that time, not the average velocity over the entire time, the average velocity over just this first interval, right? The average velocity here would just be, so this, it would be v sub I plus 0, right? Because we're kind of this intermediate velocity, plus 0, because we're stationary up here. And we divide that by 2, right? Well, v sub I is just this. So if we take this and substitute it here, we get their average velocity over the average velocity over this time interval is equal to minus g times t sub naught over 4 now. So remember, this is only the average velocity over this time period. The average velocity over the entire time period over t sub naught is actually 0 because we start and end at the same place. And this is kind of an interesting point as to how speed and velocity is different. You're probably thinking, hey, Sal, how could the average velocity over the entire time be 0 when the ball was clearly going quite fast most of the time? Well, that's the difference between speed and velocity. It turns out that the speed was, I agree with you, quite fast the entire time. But when you take the average velocity, all the times that the velocity was positive is balanced off by the times that the velocity is negative. So over the entire period, the average of the velocity is 0. And that makes sense because the ball didn't go anywhere, right? It just came back to where it started. So that's an interesting distinction between speed and velocity. But anyway, going back, and I hope I'm not confusing you, the average velocity over this time period is minus g times the t sub naught over 4. And if we were to graph it here, that would be right here. It would be essentially this. It would be this. It would be this point. Right? This is our average velocity over half the time period. And it would be equal to v sub I over 2, which is equal to this, right? So there, we know our average velocity over this time period. And we also know the time. The time is t sub naught over 2. So we can just say change in distance is equal to average velocity times time. Well, what's the average velocity? It's all this stuff, minus g t sub naught I hope you can read that. That's t sub naught over 4. So that is, let me switch some colors just so. So the average velocity is this. And what's the time? We're saying the average velocity over t sub naught over 2, not the whole t sub naught, not the whole t sub naught. And maybe if I do some examples with numbers, this won't be as confusing. So the time is t sub naught over 2. So t sub naught over 2. That's the time. And so the distance we traveled, so this distance, h, is equal to, if we multiply it out, minus g t sub naught squared over 8. So that's interesting. If I throw a ball, so this is h, and I know I'm making this really crowded. If I throw a ball and it takes, let's say it takes 5 seconds to go all the way up and go all the way down, right? Then, if I just substitute in this equation, so it takes 5 seconds to go all the way up and all the way down. And once again, this is minus g. So if gravity is actually a minus 10 meters per second, so this becomes a positive. So going back, if I say, let's see, h is equal to, so minus g is positive 10 meters per second times, let's say it takes 5 seconds. I think that's just what I said. 10 times 5 over 8. So 40 over 8. It equals 50. Oh, sorry, t squared. I was about to say something that's not right. T squared. Right? There's a minus g t naught squared over 8. So what's 10 times 25? It's 250 over 8. 250 over 8. So that's 30 something meters. What is it? 240. It's like 31 meters. So if I can throw a ball and it stays in the air for a total of 5 seconds, I threw 31 meters in the air. That might not sound high, but that 31 meters is what, 90 feet? Or 93 feet, and that's equivalent to a 9-story building. So that actually is pretty high. If you can keep a ball in the air for 5 seconds, you're pretty strong. But I want to show you something else that's kind of interesting, at least interesting to me. Let me erase some of this just because I think it's getting a little really crazy now. Let me erase this stuff. Actually, I'll even erase this stuff. I think you get it now. You can just back up and rewatch it if you ever. That's the beauty of these videos. You don't really have to take notes. You can just back it up and rewatch the video. Let's see. Okay, I think I have a lot of clean space now. So let me switch to a nice color. Okay, and back to the pen tool. Okay, so we got this. We got that the height is equal to minus g t naught squared over 8, right? But we could have also written this as, and I'm just playing around with this algebraically. This is the same thing as minus g over 2 times t naught squared, t naught over 2 squared, right? This is the exact same thing. And I was wondering, does this concept, does this look familiar? Well, sure. This is in our distance equation that we did before, where we just say that that change in distance is equal to the initial velocity times time plus at squared over 2. At squared over 2. So this term right here looks an awfully lot like this term. And this would be equivalent to this equation if this initial velocity was 0. So how does this relate? Well, another way to think about it is this distance that you're traveling, right? This distance that we're traveling up, it's also the same distance, maybe just the negative of the distance that you travel down, right? So if we said that we're starting at this point, right, We start at this point, and at this point the ball is stationary. So it's identical to just taking that ball and dropping it, right? So if we say that we're going to drop a ball from height h, how long does it take? Well, then we can use this formula. If I drop a ball from height h, so the change in distance is going to be minus h, because it's going to go from height h to 0, right? So we can say minus h is equal to the initial velocity is going to be 0,